And it's determined by the solubility of that chemical at cold temperatures. And it sets the lower limit at which that chemical can possibly melt ice. Because again, how does it melt ice? By lowering the freezing point below the outside temperature. And the eutectic sets the baseline, sets the lowest possible freezing point it's possible to get. Now, we saw a moment ago that if we just look at the freezing point of the brine, that we get misleading predictions of ice melting, relative ice melting power. Let's try looking at eutectic temperatures. It seems like eutectic temperatures should be a good guide for what is going to have the lowest effective ice melting. So this graph here shows you the freezing point curves for several common de-icers. Note that they've got this, they've got this typical V shape to them, so I can easily pick out the eutectic concentration where I've got, or the eutectic temperature where I've got the lowest freezing point. So my eutectic temperatures for some common de-icers are sodium chloride's at -6, CMA is better at -18, mag chloride's better yet at -28, calcium chloride is great at -60. So based on these eutectic temperatures, how would you rank these in terms of the chemicals that are going to have the lowest effective ice melting temperature? Well, if we look at the eutectics, we'd rank them this way. We'd say calcium chloride at -60 is going to have the lowest effective ice melting temperature. Mag chloride at -28 will be next best. CMA at -18 will be next. And bringing up the rear is sodium chloride at -6. Interestingly, if we actually test and measure the ice melting at different temperatures, the ranking isn't quite what we'd predict. What you actually see is that actually calcium chloride and mag chloride do end up being the most effective at cold temperatures, but sodium chloride and CMA switch places. It turns out that even though CMA has got a lower eutectic temperature, salt actually melts ice at colder temperatures than CMA. So two lessons here. First lesson is eutectic all by itself in a vacuum can be misleading. There's a couple reasons for this. One reason that we'll see in a moment is that the way that we measure eutectic is subject to inaccuracies in some cases. There are certain types of chemicals that give you false readings in the tests that measures eutectic. We'll talk about that in a moment. The other reason is that eutectic only tells half the story. Any chemical process depends on two fundamental factors. The first set of factors are what we call thermodynamics. Thermodynamics has to do with whether anything is even possible or not. And so for the case of de-icers, eutectic is about thermodynamics. It sets the lowest temperature limit, the lower temperature limit at which de-icing is possible. The other factor that we have to consider is what we call kinetics. Kinetics has to do with how fast a process can occur. And the things that determine kinetics are different than the things that determine thermodynamics. So eutectic does not take thermodynamics into account. So even though a given chemical might have a lower eutectic, might have a lower total freezing point it can hit, if there are factors at play that prevent it from working fast as an ice melter, which is going to be things like it has to dissolve fast at cold temperatures, if those factors aren't there, it will not be an effective ice melter. So we need to be careful about using eutectic by itself to predict relative ice melting temperatures. So speaking of ice melting temperatures, a very important and interesting question, of course, would be, for any given chemical, what is a chemical's lowest effective ice melting temperature? Now, unfortunately, I can't give you a precise answer to that question because we as an industry do not have a definition of what we mean when we say lowest effective temperature. But I want to illustrate for you the background behind that. So what you see here is a chart showing the ice melting capacities measured after 1 hour of plain salt and calcium chloride at different temperatures. And the thing I want to point out is note that it's not the case that de-icers chug along and have a pretty steady ice melting effectiveness until they hit some critical cutoff point and then drop to 0. That's not the way effective temperature works. There's not a critical cliff that they fall off at some point. Rather, note that as the temperature drops, there is just a steady decrease in ice melting capacity. So to say what is the effective temperature, we need to make some decision on where on this curve are we going to say it is quote unquote effective. How many pounds of ice do we need to melt per pound of chemical before it is quote unquote effective? I can't give you a definitive answer to that, as I said, because we need an industry definition of that. Because of, you'll hear people give estimates. Since there is no hard and fast definition, people will give you estimates that vary by plus or minus 10 degrees, plus or minus 15 degrees on what the effective temperature of a given chemical is.